I'm going to start by giving you kind of a bit of a downer that your apps are vulnerable. Now, there's probably a dozen different ways that you could complete this thought, because we're at a security conference here, but I want to talk about one specific way that I think should be fixable. So I'm going to talk about making TLS connections from one of your devices to a remote server. The idea behind TLS is that you're supposed to have a secure connection to that remote server, and what that means is that you get some nice properties. You can authenticate the identity of that server, you can encrypt all of your data so you get confidentiality, and the data can't be modified without your permission. Now, the fact that there might be vulnerabilities in how your applications are using TLS is a bit disconcerting, because you're supposed to see this nice little lock icon, and the lock icon represents all that is good and pure on the internet, even if it does tend to represent a purse a little bit. So there's been some good work demonstrating that developers actually have a difficult time learning how to use TLS correctly. There's been some good studies in the app space in particular, even banking apps, showing that these apps are vulnerable to man-in-the-middle attacks because they're not using TLS properly. And developers often turn to Stack Overflow, of course. There's been a nice study showing that when they try to do that with respect to Android security, that over 99% of the code that they copy from Stack Overflow has some kind of a security flaw in it. So that's not a good source for them to turn. And this paper in particular, I want you to remember, it showed that the most difficult part of this for developers is actually validating the certificates that they receive. There's a number of steps you have to go through to follow best practices. They often get this wrong, and so this paper called it the most dangerous code in the world when you try to implement this, and they looked in particular at non-browser software. There's one particular assertion from this paper that I want to point you to. They say the root cause of these vulnerabilities are badly designed APIs of SSL implementations, which present developers with a confusing array of settings and options. If you've ever tried to do this from scratch, not knowing how to do this and look at, say, the OpenSSL documentation, I think you can identify with this kind of sentiment. So what's being done to fix this? There's actually a variety of different libraries that are out there that you could use, some of which try to make life a little bit simpler for a developer. But we've now confused the space a bit, so now if you're a developer, you've got to try to choose the right library in addition to learning how to use TLS properly. And some of these are going to only work for some particular languages. So you've got a bit of a problem there as well. Now, warning, sorry, I'm going to make you feel a little bit worse right now. There's not much you can do about vulnerable apps on your device. So if you own a device, even if you're a system administrator over a set of devices, even if you're an operating system vendor, so you get control of what goes on that device, you have to rely on individual developers from a variety of different sources and organizations to find the flaws in their particular use of TLS, to patch their app, and then deliver that patch to you and your device. You're basically left out of the loop. Okay. And on top of that, even if they could ensure that developers are writing correct code, if we could somehow get them all the right security education they need, there's no centralized TLS policy for your operating system. So this means that a developer could choose an old version of TLS that they shouldn't be choosing, or some weak cipher suites that have been shown to be insecure, and your apps are at risk in that case. Okay, so now you're all feeling terrible about life. Let's figure out how can we solve this, because I'm asserting that this is a fixable solution. So I want you to join me on a quest. We're going to find the TLS Holy Grail. We're going to see if we can do this, okay? Now, what do I mean by the TLS Holy Grail? I mean two things. First of all, a single, simple API for developers to use so they can create secure applications, use TLS properly. And second of all, the ability for system administrators and OS or device vendors to ensure that all the apps on a particular machine or device follow some good TLS policy. Okay. So how are we going to accomplish and find this TLS Holy Grail? I know what you're all thinking. You're thinking architecture. Architecture will solve this problem for us. Now, I come from a networking background. Architecture is one of my most favorite things, and there's some great lessons we can learn from the internet architecture. First of all, we talk about layering, putting different functionality in different layers. And then abstractions, so that a particular layer can call up or down if it needs to deliver data to a different layer. And then a really big piece of this is separation of concerns. So for example, when we talk about IP, we talk about it implementing a particular service, best effort service. And any given router, if it's following the IP specification, is going to try to send packets as fast as it can. But if those packets happen to get to a router where there's not enough memory, there's a buffer overflow, we'll just drop the packet. It's not the concern of IP. TCP, on the other hand, layer on top of it, its concern is to try to take that best effort service and turn it into a reliable ordered byte stream for your application. So this all sounds great. Hopefully you're stepping back and looking at this architecture and saying there's one glaring thing missing, which is security. And right now what we do with security is we say that's the job of the applications in the application layer. They should all try to implement best security practices, and this is kind of the root of the problem that we're at here. Every individual application has to try to relearn the same lessons and re-implement the same best practices. Okay, so I promised you that we're going to find a holy grail. We're going to use these same principles, layering, abstractions, and separation of concerns, and see, can we design a better solution for TLS? So we're going to start off with layering. We're going to implement a security layer that has TLS. An application should be able to call this layer and not worry about how TLS is implemented, right? That's the separation of concerns. It's also the proper use of layering here. Then we're going to put on top of that layer the POSIX socket API. This is the most well-known, well-used, well-supported API there is for interacting with the network. So we're going to give applications that abstraction. Okay, so if we take those two things, what does that look like? Well, here is your standard POSIX socket API. I've been teaching students this API for 25 years. We always tell them, when you want to create a socket, you call the socket system call. Your first parameter is protocol family _ internet, saying I want to use internet addresses or IP version 4. Then the second parameter is sock stream. I want a reliable ordered byte stream for this. And then don't worry about the last parameter. Just set it to 0. That means you're going to use the TCP protocol. So we're going to get a secure socket API by changing that one parameter. We're going to change that to IP proto TLS, a different constant instead of 0. And that's going to signal to the operating system, oh, I want a secure socket when I connect it. Okay. On top of that, we'll use some get sock op and set sock op options so that developers configure their security. So here's an example of a program that we wrote. This is a little small web client. It just goes and fetches Google's home page. It's trying to do this securely. And you'll notice in red, there are two small changes that we had to make in order to turn this into a secure web client. We had to change the port to 443, and then we changed that 0 to IP proto TLS when we create the socket. Everything else is taken care of for us by the security layer. This is the idea of what we want to create. Okay, so how are we going to compare that to what we have to do right now? We took this same protocol, this is the same application. We wrote it using the OpenSSL library, and we ended up with 317 lines of code. And most of that is from having to validate certificates, this tricky area that users struggle with. Okay, so that's the power of choosing the right abstraction. How are we going to actually implement that particular transport security layer for us? Well, here in this diagram, you can see on the right, the application. It calls down to the POSIX socket API to create a socket. We've written a kernel module that will intercept those system calls, recognize that they are trying to use a TLS socket, and divert that to an encryption daemon that runs in user space. The encryption daemon then will implement all the best practices of how to use a particular security library, say OpenSSL, to create that TLS connection for that application and communicate over the internet. And then there's an important piece here that we get by using an operating system service. We get a lever for policy. And so that encryption daemon can check policy and ensure that any outgoing connections are going to adhere to the policy that you have set for that particular machine. All right, now I promised you I was going to follow some principles, so let's walk through separation of concerns here. The operating system is going to provide the implementation of the security layer and the enforcement of that policy. the system administrators or the operating system or device vendors can specify policy. That's going to include things like minimum TLS versions, acceptable cipher suites, even in a preference order. It could include mandating certain things about certificate validation, like checking revocation status, if you would like to enforce that for your applications. And then developers, when they write code, are going to specify configuration of that TLS connection. And that's an important point. What we're going to do is push developers to use configuration instead of implementation, so that they can specify how they want the security layer to operate, but not actually have to implement it themselves. We think this approach will lead to far fewer bugs and therefore vulnerabilities in applications. So here's an example on the server side. If you want to create a secure server, you're going to specify IP proto TLS, and then you could do things like assign a certificate chain that you're going to hand out to clients when they connect to your server, and perhaps assign a private key so that you can prove ownership of the public key that you're giving out. Now, important secondary principle here is that in our system, developers can never weaken security relative to the system policy. So if the system policy says here's a minimum TLS version, for example, they can request a greater one than that, but they can't ever request an old TLS version, or they cannot request a cipher suite that is not supported by the policy. If you take then these things that we've got here in the security layer, we've got the POSIX socket API as an abstraction, the kernel module that intercepts system calls. That also gives us a nice property of easy language support. So this isn't just for C. We were able to port this with a very small amount of effort to cover PHP, Python, and Go, just as a demonstration. And the bulk of that work was just finding where to define the new constant for IP proto TLS. That was all that was needed for PHP and Python. For Go, it was adjusting some wrappers around the system calls. We also took a couple of different web servers. We took Caddy and Lighty, and we ported them to use the secure socket API instead of OpenSSL. And to do this, we took an undergraduate student who knew about sockets, but had never seen the actual source code for these web servers before. And it took them a total of 5 hours in each case. That was mainly stripping out about 2,000 lines of code to interact with OpenSSL and putting in a handful of lines to use the secure socket API instead. Now, you probably noticed that this is creating some centralized implementation of TLS for a given device. There's some pros and cons anytime you use centralization as a solution. The con is, of course, that any bug in our implementation of the secure socket API is going to affect all applications. The pro is that if we patch that, then it applies to all applications. So we think this improves the state of the art right now, where now if there are bugs in applications, each one has to be patched individually. Here we're going to patch them all in one place and hopefully also reduce the number of bugs because developers are focusing on configuration instead of implementation. Ideally, if we can get operating systems to support the secure socket API, then they would also be devoting their resources to ensuring that their code is not got any major bugs in it. So the idea here is that if we can put Google and Apple to work, that might give us some additional advantages. And of course, with centralization, we also get easy language support, as I described, and that policy lever. You may also notice that with our particular implementation, we go into the kernel, out, and then back in. That seems a little bit wonky. You might think of a better way to implement this, but in our case, we did some performance testing of it, and there was no discernible overhead having to do that. And I can point you to a paper that will give you some details of how we ran these tests. Okay, so maybe you're thinking, wow, this is fantastic. We have found the Holy Grail. But remember, there is an old man who insists that we first must answer 2 questions before we can get over the bridge of death. Okay? So we have first one important question. How do you implement certificate validation in this architecture? You might remember this paper where I scared you and said, this is the most dangerous code in the world. How are we going to solve this problem? Well, we have another system that we call TrustBase that implements best practices for certificate validation. And so the secure socket API on the right with the encryption daemon simply has to call TrustBase whenever it has a certificate to validate, and we're removing that responsibility from the developer. we've also given system administrators some additional tools, which we call plugins, that they can use to provide stronger authentication if they desire of those certificates. So that can include enforcing revocation checking, if a developer needs to pin a particular certificate, if they want to check certificate transparency logs, we give you the ability to do that, and you have policy to be able to set those things for you. The other really interesting thing about this architecture is that we can apply these across all applications that desire to use the Secure Socket API. So if you've heard of Google's CRL set checking, that they bake that into Chrome, we've got a plugin for that, and we can check their same CRL set service and apply that to all applications, not just browsers. All right, now we have a second question we've got to answer. How do you handle client authentication? That's a really thorny part of TLS. We want sometimes to be able to give certificates to users, not just to services and servers. So how are we going to be able to make that work? Well, you might be thinking, no problem. We can just turn users over to certificate authorities. We first of all have to tell them what a certificate is, which kind of certificate they want, how to choose a certificate authority that they trust. And then if they choose a certificate authority, I don't want to bag on DigiCert in particular, but they would turn around and give you, here's a 42-page document with instructions on how to obtain the certificate from them, how to configure it with a particular application. You have to configure each application or each browser individually, and you have to hand over your private key to that application so it can authenticate on your behalf. All right, we think we can do better than this. You could say, well, let's turn to the FIDO2 standards. They've got this really great web authentication standard they're working on. I think this stuff is fabulous. That is punting authentication to the application layer. Maybe that's the right architectural choice for you. But we want to see, can we do something better with TLS client authentication? And what would that look like? Could we make it as usable as the web authn standards appear to be? And we also have LeBron James here reminding us, what about the architecture? You promised me this was an architecture talk. So how would this actually work with this TLS architecture we've been working on, the security layer? So here's what we have right here. We have on the left a server that is using the Secure Socket API, and it's making a TLS connection with this client application. And when the server asks for client authentication, the Secure Socket API is able to intercept that request, and rather than giving it to the client app, turn to an authenticator app, a separate app, which is going to hold private keys separately in a trusted hardware module of some sort, and also provide a user interface to the user to say, do you want to authenticate with a client certificate to this particular service? And if the user says yes, then the authenticator will work with trusted hardware to get a certificate that we can use to complete that handshake. And we've divorced that from the client application. So the client application doesn't need to be built with this kind of logic with each individual application. We can support client authentication regardless of whether you've baked it into your app or not. Now, in this case, I'm showing you that the Authenticator app is living on top of or inside of the same device, but we've also pulled that apart, and the Authenticator app can be a separate device. In our case here, showing you a smartphone, and that can communicate and complete the handshake for you. So I'm going to walk you through this very briefly, how these steps would work. Step 0, you need to pair your phone if you're going to use a separate device with your laptop. We have a prototype of this where we scan a QR code off the laptop's display, so we make sure we're pairing with the right device and securing that channel. Then if a server wants to, if you connect to a remote server using TLS, and that server wants to make a certificate request to you to say, please authenticate to this service, then we direct that authentication request to your authenticator device. The user is given a simple yes, no, do you want to log into this particular service? And if they say yes, we can sign the certificate data, hand that off to the laptop, and the laptop, in this case then, would complete the handshake on your behalf. You've now authenticated a separate device. You've kept your keys separate, so we have separation of concerns here. The policy is given to the user in this case, as opposed to the system administrator, because they can choose how and when they want to log in. And you can even de-authenticate or deactivate that authentication remotely for this device. So if you're going to use a device in a public space that doesn't belong to you, for example, you can log in securely, you keep your credentials safe with you, and you can turn off that authentication whenever you want and log out that device so it no longer can impersonate you. All right. Now, we've solved a big piece of that puzzle, but what about getting client certificates to users? That's a really thorny problem. We've got two particular ways that we're working on to solve this problem. One is that we have a prototype that automatically creates certificates for you when you register for an account with a service. So you're going to a service and it says, you want to create an account, simply prove ownership of the public key that you presented, and then they will then sign a certificate for you, deliver that certificate to you, and you can represent it at a later point in time when you want to log in. So we've got a certificate that is bound simply to a particular service or site. Now there's some downsides here, of course. If I somehow lose my authenticator device, I lose my phone, then I lose access to my accounts. So we're building a backup system for this, and my lab is mostly in usable security, so we're trying to figure out how can we provide usable ways for people to back up and be able to recover accounts in situations like this. That's the first way. The second way we're working on building right now is a system we're calling Let's Authenticate, modeled after the Let's Encrypt service for issuing certificates automatically to users for websites. Here we're going to automatically issue certificates to individual users, and we have a couple of ideas. One of them working on is proving, again, ownership of your public key, but then also proving ownership of your email address, and the service can bind those together and sign a certificate for you. And we can do this automatically for users for the most part. We simply have to have the user check their email and get a code, which they're used to doing already. Now, this has some different properties compared to the previous solution we showed you. First of all, if I lose my phone, well, I can easily replace that with a new phone and reprove ownership of my email address, get a new certificate, and still have access to my account. So that has some nice properties for users. But, of course, has the downside that we now are adding even more importance to ensuring the security of your email account. So we're working on looking at those different trade-offs. This particular one is very similar to what we do today, where people can reset passwords through their email accounts. The alternative is to somehow teach them and help them protect their private keys because they are irreplaceable. And so we're looking at the trade-offs of those two kinds of systems. Now, if I take all that stuff together, that lets us reduce that 42 pages of how to use certificates to 1 or 2 clicks for the users. So that's what we're trying to get here, is to get TLS certificates as usable as a 2-factor auth app on your phone. So you might be thinking, wow, this is amazing. Secure Socket API is the holy grail. We found it. Okay. What I hope I've convinced you of is that architecture is the holy grail. That when we're designing systems like this, we want to look very carefully at principles that we've learned over the years. We want to look at layering to isolate applications from implementations of complicated software like TLS. We want to try to choose the right abstraction. Abstractions give us usable security for developers and fewer vulnerable applications. And we want to look at separation of concerns to decide where do we want to place that implementation. Can we somehow give developers a configuration interface rather than requiring them to implement security policy? Can we separate policy out and give that control to users, to system administrators, or to operating systems vendors? And can we be really careful about where we place those keys and ensure that those keys are in a safe place? I would love to have you help me continue this quest. I don't think by any point we're finished. You can visit securesocketapi.org to find papers and code. We would love to have you help us, whether you're a developer or an OS vendor or a researcher. There's lots of work to be done there. If you're a user, hopefully you've come out of this talk and said, I really want to ask for policy control. I think that will make me safer. Thank you very much.